Hi, my name's Nikhil Patel,
And I'm Jacqueline Pai.
and we are here to explain to you about
Limits.
Now let's start off with the definition of a limit. The limit as x approaches c for any point on a graph, on the left side of the function, f of x, has to equal the limit as x approaches c on the right side of that same function. So here we have a graph that Jacqueline will explain.
Okay, so on this graph we have a point 1, 3. So to show that this is a limit that it works, as the limit approaches the point from the left, the right, and as it approaches the point from the left, you see how they both go to this one point right here, which proves that this exists and is a limit.
Next we'll explain how to solve a limit.
There are 3 ways to solve a limit. There you can solve either numerically, graphically, or algebraically. So our first way of solving would be numerically. So in our x values, we're going to put numbers that are approaching what the limit approaches. So in our case, it would be 2. So instead of putting exactly 2, you put numbers, 2 approaches, which would be 2.1, 2.01, 2.001, 1.9, 1.99, and 1.999. So as the x value approaches these numbers, our y values are slowly going to approach one number, which in this case would be 4.
Now to solve it graphically, you're going to place a point at where x is equal to 2. So you put 2, we place it into the graph, and you get 2, 4 as the point. Now to see if it's actually a limit, if the limit does exist, you have to find if the limit on the left side equals the limit on the right side. So as you see, the limit as the left side, on the left side of f of x approaches the same limit on the right side of f of x, which is 4. Now to solve it algebraically, first of all, we need to make sure that the function is continuous at that point, which is what we'll explain next. But after knowing if the function is continuous, we can just simply plug in 2 for x. And behind the scenes, what's actually going on is we're just finding it numerically. We're just finding x values closer and closer to 2, but ultimately we're just substituting 2 in for x if the function is continuous at that point. So next we're going to explain continuity.
You can either have a discontinuity or a continuity. So for discontinuities, there are 3 types. You can have a jump discontinuity, a removable discontinuity, or an infinite discontinuity. So in the case for a jump discontinuity, the limit as it approaches the numerical value from the left and from the right, they do not equal each other. So it wouldn't be continuous. For removable, the numerical value would be undefined. So there would be a hole where your numerical value would have been. And for infinite, it's the y values, they approach negative or positive infinity.
Now to explain a continuous function, the formal definition is as the limit of x approaches any point, we'll name it c, of f of x, it has to equal f of c. This means if you put in, for example, if c would equal 2, in this example, you get 2, 4. Now the limit on the left side and the right side both approach 4, so we know the limit does exist. And if you put in f of c or f of 2, then you'd also get 4. So that is when you know a function is continuous at that point.
Okay.
So for this, we'll talk to you about unbounded growth and indeterminate form.
Okay, so for unbounded growth, we have the limit as x approaches 4 of x plus 2 over x minus 4. So in this case, if you were to plug 4 into the denominator, we would get 0. But if you so that would be in indeterminate form. However, if you put in the numerical values that are close to 4, for example, 3.9, 3.99, 3.999, or 4.1, 4.01, or 4.001, you would get that the limit approaches infinity, which is due to unbounded growth.
If you put in this function, limit as x approaches 0, you get of x over x, you get 0 over 0, which is indeterminate form. However, you can still find the limit of this, you just have to plug in, or find it numerically or graphically. So next we'll explain how to solve limits as x approaches infinity. So for this example, we have x minus 3 over x squared plus 2. Normally when you want to solve limits as x approaches infinity, you want to use incredibly big numbers. These numbers include million, billion, or trillion. So if you put in million in this function, you get a million minus 3, which is pretty much just a million. And you get a million squared plus 2, which is pretty much just a million squared, which reduces to 1 over a million. 1 over a million is an extremely close value to 0. And this is really only amplified with bigger numbers like billion or trillion. A billion minus 3 is pretty much just a billion over a billion squared, or a billion squared plus 2, which is just pretty much a billion squared, which is, when you simplify it, 1 over a billion, and same thing, it's even closer to 0. And a trillion is the exact same thing, it's just closer and closer to 0.
So as you can see by our graph, we have graphed the function x minus 3 over x squared plus 2, and you can see that no matter what value you put in, you're going to get basically x equals 0.
Yeah, and this is an extremely zoomed out graph of our function, and in the end, you can see it's basically x equals 0. It's basically the x-axis. Okay, so we're going to explain one-sided limits now. In our example, we have the limit as x approaches 2 on the left side of x squared.
Okay, so to numerically solve that, we're going to use numbers that approach 2 but from the left side. So we're going to have 1.9, 1.99, 1.999, and if you plug these into our function of x squared, you're going to get 3.61, 3.9601, and 3.996001, which all approach the number 4.
To do this graphically, it's also the same thing as you would do it with a two-sided limit. You plug in, you put the point 2 into the function x squared, and you get 4, and then you make sure, or you try to see if the function leads up to that point on the left side only. Of course, if there was limit as x approaches 2 on the right side, with the positive right here, with the positive sign, it would be on the right side. But because our example is only with the left side, we're approaching it only on the left side. So as you can see, the arrow shows how the function gets closer and closer to 4. The y values get closer and closer to 4 on the left side. Now, also to do it algebraically, it is the exact same way you would do it with a two-sided function, two-sided limit. You plug in 2 into the function, but behind the scenes, once again, you're pretty much doing it numerically. You're pretty much finding numbers that are closer and closer to 2, and then you find the y value for that, and which it does approach 4. So next, we'll explain the intermediate value theorem. This theorem pretty much says that if a function is continuous at every point through an interval from a through b, every x value through that interval will be consistent in that graph. So for example, we have a question that asks, does f of x have a value at x equals 0? Now, we wouldn't know just by looking at this graph, you can tell it does, but we know for sure that it does have a value at x equals 0, at least one value of x equals 0. Because if we take the point -1, or the x value -1, we see that the y value is a negative number. And if we take the x value of 2, we see that the corresponding y value is a positive number. That means that between the interval of -1 and 2, if the function does hit the the x-axis at least once. And that means that f of x does have a value at x equals 0.
Okay.
So next we'll explain the instantaneous rate of change, which is pretty much just the slope of a tangent line on a function, and how limits can be used to find those.
Okay, so you can use average rate of change, which is the slope of a secant line of 2 points of a function. So you can either use the equation y2 minus y1 over x2 minus x1, which is also equivalent to f of x2 minus f of x1 over x2 minus x1.
Now this average rate of change equation can be used to find the instantaneous rate of change of a function. So we have to find the limit as h approaches 0 of f of x plus h minus f of x over x plus h minus x. As you can see, this equation by itself without the limit is pretty much just this equation, except it has an h. The h, what is the h? The h is a distance between from the x value, which is what the point we're trying to find at instantaneous rate of change, is the distance from the x value. So if, for example, if x is equal to 2, and we're trying to find the instantaneous rate of change at x equals 2, h could be any number, and that's just the distance from x equals 2, or from 2. So with the limit involved, we can see how h of 0, or h approaches 0, means as the distance gets closer, as the distance between this x value and this y value and this y value gets closer and closer to each other, we will find an instantaneous rate of change.